I'm Perdita Barran. A lot of people call me Purdy. I'm a professor of mass spectrometry in the University of Manchester, and my main the main thing I do is I make measurements on the mass of molecules, and also I measure their shape, and I build machines to do that. And when I say actually I have a great team of people who does that. But my entire research career has been in that area. I've always built machines or built parts of machines, particularly the parts where we make the molecules, to then look at them in a way that is really detailed. So mass measurement, we're weighing molecules essentially, and every molecule consists of atoms, and we know what atoms are made of. They're made of they've got each of them discrete weights, and so we can predict when we make a mass spectrometry measurement what we're doing. So I started off, and I've got some props, I can show you the props. So I started off at the University of Manchester, and I did 2 undergraduate projects there, which were great. And they were, one was working with someone called Gareth Morris, who's still my colleague, which is rather wonderful. He's an NMR spectroscopist, and I really started to learn about making measurements on molecules with him. And I also worked in a surface science group with Gareth Thornton, also looking at molecules, but now on surfaces. After I'd finished my undergraduate degree, I went to the University of Sussex, and the reason I went there is shown by this. So I think probably most people know what this is. It's a structure of a molecule, and the molecule is C60. So as an undergraduate, again at Manchester, I'd been asked to write an essay in second year, and it was about an invention, and I wrote it on the discovery of these molecules by someone called Harry Kroto, and the molecules are fullerenes, and he had been involved in some research to create, again, design a source to look at clusters from different materials. And when they looked at clusters from carbon, they found that they had a particular stability when you had 60 carbon atoms. And so that discovery had happened, and I went to his lab to start to do some other things, to try and put some metal atoms in. And I loved it. I absolutely loved it. And I loved all sorts of things about it. I loved the fact that when you are doing science as opposed to learning about it, you are creating something. You don't know what you're going to find. And I loved the machinery. And I don't really know in my background before that why I was going to love so much making the instruments and understanding the instruments to look at the molecules. I like cooking, and my parents had always encouraged me to cook. But I grew up in an urban. I grew up in London. I wasn't spending an awful lot of time with machinery. I certainly helped out my parents with different things, but I just loved that machine aspect. So another time you can get to see my lab. It's full of machines, and we have a lot of instruments. They're quite noisy, and we use them to look at molecules. So after my time in Sussex, I had been there looking at molecules including C60 and others in things called molecular beams. And when you generate a molecular beam, one of the reasons you do it is because you want to control the temperature of the molecules you're looking at, and molecular beams lower the temperature of the molecules, and that means you can understand some really fundamental things about what they're like. Except that, so these molecular beams were like around about 30 Kelvin, so really much colder than we are now. And I started thinking to myself, well, wait a minute, is that where life is? Is life really at 30 Kelvin? No, it's not. Life is at 300 Kelvins. It's here. It's in the world about us. And I also started thinking that I was wanting to become a scientist. Well, I was sort of becoming one, but I wanted to maybe permanently become one. And that it might be better to look at molecules that weren't quite as esoteric as carbon and metal clusters, and maybe had a bit more practical relevance, and that would be biological molecules. So those 2 bits of information, and wanting to look at things not at low temperatures and wanting to look at things that were biologically relevant, were things that I, as an undergraduate, I was not interested in. I was very fundamental physical chemist. So I moved to California, and I started working there in a group run by someone called Mike Bowers, who's a fantastic scientist, and he had been one of the pioneers of a technique called ion mobility mass spectrometry. So I'm going to do an experiment to show you what an ion mobility mass spectrometer does. So mass spectrometry measures molecules according to their mass. Okay, oh, actually, I'll do it with these papers. And mass is easy, we understanding it's weighting, it's weighing things. So if I had two bits of paper and these are identical A4 pieces of paper, right, they would each have exactly the same mass. So our mass spectrometer wouldn't distinguish between them. And actually they are identical. But imagine that these actually were two proteins or the same protein, but one of the proteins was folded up and one of the proteins was extended. And that's what happens when proteins denature. And it's also what happens for proteins that are involved in neurodegenerative disease. I'll come on to that. So if I have a mass spectrometer and I had these two forms of the protein, they would weigh the same. And so the mass spectrometer wouldn't tell me how much of the protein was folded and how much was extended. But if instead of, and in a mass spectrometer, I'm looking at molecules in a vacuum. So I measure how fast they move in a vacuum. And so in a vacuum, these would both move at the same speed. But if I was in an ion mobility spectrometer, I wouldn't just have is a vacuum, so mass spectrometer, vacuum and an electric field. Okay, electric field moves them, and they're in a vacuum, so there's nothing to stop them going, so they move. In an ion mobility spectrometer, there is an electric field, and there isn't a vacuum. There's some gas, and there's the amount of gas that's there we know about. So there's gas in this room, so we can do this experiment. So I'm going to drop these two molecules, well, papers, but anyway, I'm going to drop them. And you know, of course, and you saw that then, I'm going to do it again, do it slow, that the folded protein fell much more quickly because it had a smaller surface area and it underwent less collisions with the air in this room. And so it got to the detector, which was the floor. So now the electric field is gravity and the detector was the floor. And it got to the detector faster than the unfolded piece of paper. That is what an ion mobility mass spectrometer does. And around about the end of my PhD, I've been looking at fullerenes. I saw a talk by a man called Martin Gerald, and he was looking at these carbon clusters with ion mobility mass spectrometry to understand how they form the nice circular shapes that they have when they're large. And I just fell in love with that technique. I just thought, that's what I want to do. This is going to give me a direct measurement. And going back to the temperature thing, it's going to give me a direct measurement at a temperature that I can control, because the gas that we send the molecules through, we know the temperature of that. And we know the temperature of the ions because of the number of collisions with the gas. So at Sussex, where I did my PhD, I built my first ion mobility instrument. It was okay. I've built better instruments since. It was all right. And then I went to California to work with Mike Bowers to really start to look at biological molecules with ion mobility mass spectrometry. So that was pretty good. And at that time, I remember I'd been working on clusters. There was the beginnings of, and this was in the early 2000s, there was the beginnings of a realization that there were diseases that were not genetic in origin, but were based on proteins and were based on a change of shape in proteins. And those diseases collectively are known as prion diseases, or protein-only diseases. And we know many of those diseases, and they are neurodegenerative diseases such as Alzheimer's and Parkinson's disease. So both Alzheimer's and Parkinson's disease have a particular characteristic in the brains of people who suffer from them, and that is plaques that are formed, and those plaques are full of aggregated proteins, also some lipids, other moieties, and those aggregated proteins were proteins that were once maybe folded and they were fine and they would normally be discarded by cells, but for reasons that aren't fully known, in people who have Parkinson's disease and Alzheimer's disease, those proteins are unfolded, and instead of being degraded by the cell, they start to cluster together and they start to form lumps that are they can't be cleared by the cell, and these lumps start to form and they eventually form these plaques. And ion mobility mass spectrometry is really good at looking at the very first stages of that assembly process. So the change in shape of the protein from its normal folded, happy protein normal state to an unfolded state that then allows this accumulation to occur. So I've got a protein structure too. This is insulin. It's a beautiful molecular molecule of the protein insulin. And people who have diabetes will have to inject insulin to help to control their regulation of sugar. And it isn't the case anymore, but some time ago, people repeatedly injected in the same place. They would be putting insulin probably into their thigh or their arm, and they would get something called insulin-dependent amyloidosis, where insulin, the drug that they were putting in, would start to accumulate in the same way that other proteins accumulate in people who have Alzheimer's and Parkinson's. And so one of our early model systems that we looked at with this technology was indeed insulin, to try and understand its aggregation. So I now had a technique which was not just mass spectrometry, but eye mobility mass spectrometry, and I also had some ideas about the sorts of things I wanted to look at, and they were biological systems. I wanted to take what I knew from clusters and apply it to proteins, and use this eye mobility technique to do that. So then I was like, okay, here I am, I've got all these ideas and I know what I want to do, and so I better start applying for funding. So I did, and it took some time, and I was doing a postdoc, so I was happy, and science was going well, but I really wanted to start my own group. I wanted to run my own team. I was getting a little bit, no, I worked for great people and they were always encouraging, but there's a point when you really want to do your own thing. So I was very fortunate, and I got a fellowship from the EPSRC, the Engineering and Physical Sciences Research Council, which gave me 5 years funding to start to explore this area. And I took that fellowship at the University of Edinburgh. That was great, and I built my first eye mobility mass spectrometer in my own group, having built one or two before, working for other people. At this point, I started really to collaborate with industry, and particularly with a mass spectrometry company, which was called Waters, well, it's called Waters, but also Micromass. And they were beginning, because at this point there were no commercial eye mobility mass spectrometers, so you had to build your own if you wanted to do this. But they were starting to get interested. There were a few labs, like Bowers' lab, I already mentioned where I did my postdoc, Martin Gerald, who'd done the cluster work. There were a few labs who were doing some really excellent work, and particularly someone called David Clemmer, who was greatly inspirational to me. And he was looking at proteins. He was using eye mobility to also look at other complex mixtures to really understand their structure-function relationships. And so Waters at this point was starting to think, oh, maybe there is some commercial benefit in this, and that was just when I started. And so in 2005-06, we built our first eye mobility mass spectrometer, and in 2007, Waters launched the first commercial one. And so that was really great, and it's now become a much bigger field. So when I started, it was a field where there was probably only about 10 labs in the world that had such technologies. Now there are many, and that's great. It's been a good field, and it's been a good thing to be involved with. So here I am now with a technique and with many systems to study. Aggregation of proteins has been a big area. Looking at transformations in protein structure, folding and unfolding has been a big area. And that was all the way I was, and I was doing this in Edinburgh, and I had great collaborations, and then a job became available at the University of Manchester, and I think I'd always wanted to come back here. I'll show you one more. I've got one more prop to show. So when I was a PhD student, I didn't have very much money, because that's the case with PhD students, and I worked in a bar at Sussex University, and there was a promotion. Can you see that? So there was a promotion, and it was Boddington's beer, which at the time was not something you could get in many places outside of Manchester, but it was coming to Sussex. And the promotion meant that we got this keyring, and so this keyring is, well, it's 25 years old, and it sort of looks like it. And I've had that on my keys for the last 25 years, and I think it was, although I hadn't quite realised it, I think it was symbolic of the fact I really wanted to go back to Manchester. So in 2012, I was fortunate enough to get a chair of mass spectrometry at the University of Manchester and come here. And funnily enough, that year, something else really remarkable happened, and that was that Joy Milne, who is a wonderful lady, who is now my postdoc. So she's a part-time postdoc at the University of Manchester and an honorary lecturer. But at that time, she was a retired nurse whose husband was very ill with Parkinson's disease. And she approached my colleague, Thilo Kunath, at a public talk he was giving to at the end of his talk, ask him a question which wasn't really relevant to the talk he'd given, although he does wonderful work on stem cell models of Parkinson's disease. But it was this. She said, Tilo, that's wonderful, the research you're doing, but why aren't you doing anything about the fact that people who have Parkinson's disease smell differently? And Tilo was absolutely shocked by this question. It wasn't relevant to the talk he'd given, and he also misinterpreted it. It was like an eat, shoots and leaves misinterpretation, because one of the early effects of people who have Parkinson's disease is that they lose their sense of smell. And so he thought she was saying, why can't they smell? But she wasn't. She was saying, why do they smell? And he left it at that. He spoke to her a bit, but he left it at that. He knew her first name. She said, my name's Joy. And then he rang me up. I think he rang me up the next day, and he said, Perdita, what she's talking about, it's could you detect this odor? And I said, yeah, mass spectrometry could detect that odor. Odor is molecules, and mass spectrometers detect molecules. And so we started thinking about what to do. And I had a really brilliant Brazilian student who was on a placement in my group at the time, and I had him wearing gauze under his armpits, because you think, smell, it's going to come from sweat, isn't it? He put gauze under his armpits. He ran up and down the Pentland Hills to get sweat, to then develop some methods for extracting volatile molecules, volatile that go through the air. And Tilo had we thought well, actually, I have to confess, when Tilo first told me about it, I said, maybe she's just smelling old people and thinking they smell like her husband. Her husband had Parkinson's disease. He had a distinctive smell. And my first thought was, nah, it's a psychosomatic thing. She's associating the smell of her husband with other people, and it's just an old person smell. Tilo had met her, and she's very convincing. She's a great friend of mine now. She can. But he and I thought of different experiments that we could do to make sure that it really was the odor rather than the symptoms of Parkinson's that she was seeing, the movement symptoms and associated with the smell. So the experiment was this: we recruited some people who had Parkinson's disease and some people who didn't, and there were 12 in total, 6 with and 6 without, and we made them wear t-shirts, and we took the t-shirts off them and cut them in half and put them in bags and gave them to Joy to smell. And Joy was almost 100% correct in diagnosing from these t-shirts the odor of Parkinson's. It was remarkable. It was really remarkable. There were 2 other remarkable things. So she could do it, and she couldn't just do it. She could put the people back together. So she knew the 2 halves. She said, that's that person, and they have Parkinson's disease, and she was right. But the other remarkable thing was, one of them, she said, had Parkinson's, and they didn't. And we didn't understand that, but we thought, well, there's a lot of smell in the room, and maybe she's... And actually, then that person came back to us 9 months later and told us he'd been diagnosed. So that was really remarkable, because Joy's story is that her husband had a change in his smell when he was in his early 30s, and 12 years after Joy had noticed this change in smell, he was diagnosed with Parkinson's disease. So way before any other symptoms or any other apparent symptoms, there was this distinctive odor. And so Joy and her husband Les knew that this meant something, and so they worked hard to think of a way of finding scientists to understand it. The other remarkable thing about the t-shirt experiment actually has been the biggest thing, and that was that the smell was not in the armpits, as I had predicted, as you would predict, but under the neckline. And the reason it was, and in fact the armpits didn't smell very much at all of Parkinson. So the reason that it was in the neckline is because from our hair and in the middle of our back and also in the T area of our face, we secrete a lot of a substance called sebum. And sebum is something you only really know about when you have spots, right? And you get spots, you say, oh, I need to clean off this greasiness. But sebum's a really remarkable substance that's oily, sort of waxy acids and esters and lipids, and it, I believe, traps odor. And so we now run a clinical trial where we sample from people their sebum, and we analyze the sebum to see what components are in it. And we compare sebum from people who have Parkinson's to people who don't. And by doing that, we have distinctive patterns of volatile and actually non-volatile molecules that are distinctive of people with Parkinson's. And so from Joy's nose, oh, and to do that, the way we brought Joy back in, which is actually really good, is we have a special instrument called an odor port GC mass spectrometer, right? This is an instrument that's used in perfume houses because sometimes people want to know, they want to put musk or rose or something into a perfume. And when we do mass spectrometry, we separate molecules by their movement in a vacuum, but we also perform chromatography, where we separate molecules based on their affinity to a particular surface. And often we do both of those when we've got a complex mixture like an odor, because we want to give each of those molecules an identification. So how long do they go through the separation part of the chromatography column, and what's their weight? So in an odor port mass spectrometer, after the chromatography separation, there's a T-piece, and the molecules are split. Some go to the mass spectrometer to be weighed, and some come to the nose, and this is Joy now, to be smelt. And Joy, or whoever the odor port person is, clicks on a button when they smell a smell that they think is distinctive. And so we took sebum from patients, and Joy sat smelling the molecules as they were being separated and weighed, and clicked a button to tell us when the Parkinson's odor was strong. And that was a really extraordinary experiment. I never thought I would do that experiment, and it allowed us to address the odor and to say that the odor is associated with this signature in the mass spectrometer with these molecular species. So that's been an interesting journey, and it's ongoing. We are able now to really diagnose Parkinson's pretty well. If we add in some clinical indicators, for example, tremor or bad sleep, which is a big feature of Parkinson's, particularly early on, then we have around about 95% accuracy of detecting Parkinson's, which is far better than any clinical method. So that's the journey. We weigh molecules, we measure their shape, and we detect Parkinson's disease from sebum. It's been good. Thank you for listening to me, and I'll see you around campus sometime, I hope.